So, and last lecture, we also introduced like the idea of feature transformations. Like that was sort of a very interesting, like I think super crucial lecture because it allows us to model nonlinear relationships with the linear regression model, right? Does anybody sort of remember how that works? So wait, give me a sec. So remember we talked about feature transforms last lecture, right? So how does it work?
It would allow you to if you can make a feature transform, which is like an equation, and then have that as like an extra piece of the input vector, which would allow you to I'm not explaining it well, but it allows you to have basically an extra parameter. So with a like slope point formula, for instance, you could graph something that would normally take a quadratic.
Okay, yeah, hitting on the main points. So to be more precise about it, right, and to correct like a small misconception there. So a feature transformation is merely a function, right? It's just any sort of math function in which you take a set of, or you take an input point, right? And this input vector is some sort of n-dimensional vector, right? And you map it to some output vector. So it's a function. Remember, we said it was a function phi that maps from Rn to Rk, right? You're given an input Rn, right? And I give you a vector of size k. The misconception to correct is that you said it increases parameters. That implies that k is greater than n, but that's not necessarily true. It can be anything, right? In the lecture, the motivating example was like we wanted to produce a feature transformation, right, that increased the dimensionality of our data set, which allowed us to model this nonlinear relationship, right? This quadratic relationship. If you remember the quadratic curve that I was trying to draw, right? And I was like, okay, you try to fit a line through a curve, right? You try to fit a line through this quadratic equation, it's cooked. No matter how you do it, it's cooked, right? You can't do it, right? Because fundamentally, the data assumes a quadratic relationship, but your linear model is, well, linear, right? There's not enough expressivity. There we go. I can't English today. There's not enough expressivity in the model to capture this relationship, right? And so to go back on like what we were talking about in previous lectures, there's a strong inductive bias on this, right? Like namely, we are constraining the form of this relationship, right, to be linear. And so does everybody remember that? Are we good? Good, perfect. Okay, yeah. Because I sometimes see a head tilt and I see the head tilt as like, like I'm not sure if that's like a question, so I always like to probe. So if you have a question, feel free to ask. No problem. I also like slow head tilts where it's like, like I'm starting to get that. I like watching the facial expressions of people. Hopefully, make sure everyone gets it. Yes.
Can you please repeat that last bit?
So remember, we talked about like lines fitting through quadratics, right? And you can't do it because a line is not a quadratic, right? It's too weak. And by like the expressivity, like how the types of relationships this can represent is limited versus a quadratic. Quadratic can express everything that's linear, right? Because y equals ax squared plus bx plus c. If your a is 0, then you have a linear model, right? So in other words, like your line is not as expressive as your quadratic model. That's all I'm saying. Yes.
So then we're essentially just using phi as a wrapper function around our original linear regression to make it more expressive.
I remember you asked this question last time. To be more precise, we are applying phi onto the data set, not onto the model.
Oh, so we're applying phi to the data set to make it fit the line better then. Or
the line fits the data.
Right.
Remember, a linear regression model is a class of models, right? So it's like any sort of theta 0, theta 1 data, right? Or theta 0, theta 1, x1 data. Right?
Like that,
So I have like some sort of XY, like you can imagine that this relationship was an XY data set with a bunch of data points, right?
Yeah.
And then so it looks like a tabular data set, XY, right? And then what I'll do is for each X, I will apply phi, so I'll calculate phi of x, and so that produces a new, like, in this case, like I would, well, I would define a feature transformation 1x x squared, right? And like use for every x, I get 1x squared, right? And that gives me like, so every row, every data point corresponds to a new data point in this transform data set.
Right, okay.
Right? And then from there, like when I plot this, this is now like, well, like I can sort of disregard this one column because it's a constant, right? When I plot this three-dimensional graph, right?
Yeah.
Or when I plot these three-dimensional points, my bad, right? When I try to use my linear regression model, I can fit a hyperplane through it, right? So what was initially unmodelable effectively, right, via this was now suddenly modelable via this new transform data set.
Right, and there's, I assume there's different, you can use different fees, different transformation, depending on the shape you want to make, whether it's
Precisely.
X or
First,
natural log of X or.
yeah, but the difficulty then is like, well, like how do you for any sort of like really complicated data set, like how do you choose the feed, right? Like
Right.
what feature transformation do you choose? And a lot of and so what the conclusion we sort of stumbled upon at the end is like, okay, like it's kind of impossible, right? Like like if you're a domain expert, then okay, like for example, the example I've been using next to problem is like how the relationship between like your zip code, your median family income, your like whatever, like your maybe education or whatever, your years of education, and use that to model like housing, like house prices, right? So something like that. Like if I'm like if I do real estate, then it's like, okay, like I might know some sort of fee, like I might implicitly know some sort of fee, right?
Right, you have.
But like you have domain
Yes.
knowledge, you have domain knowledge, you have an educated guess, right? But if you're, but if you're me, right?
Right,
I don't do real estate.
yeah,
How
exactly.
am I supposed to know this, right? Like, and so defining a fee is different, right?
Okay.
And that's the sort of entire problem, because if you already knew the fee, then you wouldn't need,
Yeah,
you wouldn't need, you already know. So in a sense, it's like kind of contradictory. It's like there are limitations, right? Fundamental limitations, right? To using a feature transform, and like the hope though is that this is a good idea. The idea of like increasing the dimensionality of our data points to make it, well, modelable by function, right? So and in fact, it's like if you remember like what a neural, or how do you say it, like if you have looked at neural networks before, right? I'm sure at this point, like you go through your 3 blue 1 brown video, everyone like sees like the like columns of nodes and stuff like that, right? Like every column, every sequential column you're looking at, he doesn't really mention this in his videos. I remember like watching that video a lot. I loved it so much. It is one of the reasons why I'm doing this, because I love it, right? But in his videos, like because I also referenced it while I was doing the notes for this, like he sort of kind of omits the fact that like those are feature transforms, right? Every column is a feature transformation, right? You are transforming your input representation, right, into like a sequence of input representations. Okay, but yes, this is all recap. And okay, we didn't go over regularization, so maybe we could go over that like after, but it's important, but sort of tangential to the lecture today, so it's fine, whatever, no problem. And we've also talked about cross-validation before, but that was like 2 lectures ago, yes.
So, I'm sorry if it's redundant, but just to clarify, so feature transformation is literally just changing the shape essentially of
Yeah, like defining a function to change the shape of your data effectively.
Okay.
Or to induce higher dimensionality, or maybe not, right? You can reduce the dimensionality using this using your feature transform, right? But the idea is like you want to make you use this feature transformation to make your data like, well, more like modelable according to the constraints of your model, right?
Mhm.
My model here, my linear regression model, was constrained to the idea, the assumption that like the relationship between my input variables and my output variables is linear, right? My data isn't.
Mhm.
So I need to somehow change my data to be linear in a sense, right? But I can't just like flatten it. That makes no sense, right? Like, so what I do is like induce higher dimensionality. I make it linear in some extra dimension. Like,
So,
but this effectively is redundant information over this. Right? I've like manually introduced extra dimensions. Right?
so is the phi learned?
No, like in this case, what we're just saying is the phi.
It's fine.
Pardon?
It's a five.
Like we define it.
Oh.
That's what that. So that was what my that was my like how is that how I was answering your question. Sorry, what's your name again?
Liam?
Liam. That's how I was answering Liam's question. Right. Okay. Does that make sense? Okay. Okay. So where were we at? Okay. So now we'll sort of go through the linear classifier, right? And so this sort of builds towards again like neural networks. Right? Everything we're sort of doing is in service towards like having you understand the neural network, right? So, linear classifier, as the name sort of suggests, well, there's two parts, right? Like it's a class of it's a class of linear models. Well, we'll talk about like where the linearity is, and then we'll talk about like well classification, right? So can anyone sort of like remind just as a reminder for only the first day of lecture, what is classification?
It's mapping some input to some specific class that you already have defined,
Correct. Yes.
or
Correct.
I think some they make classes.
Right. Indeed. Like you have like if I'm trying to classify like if I am trying to classify but like when you say the word classify, like classify an object, like if I'm looking at a chair, I'm classify it as a chair, right? Like I've given it like a discrete label. So yeah, that's a classification problem. Whenever you have some sort of data set D, right? Remember, this is still in the domain of supervised machine learning, and so you have some data set D in which you have some sort of which you have tuples of xi yi pairs. Remember, like this sort of D equals xi yi, right? It's a tuple of them, right? And this represents a single data, right? And each xi, remember, can be continuous. It's in the space of Rn, which is n-dimensional space, right? So in other words, each point is represented as a vector of n components, right? And then, but the yi's, as I said, for classification problems, have to be discrete: zeros, ones, twos, threes, fours, right? Like actual discrete numbers, they cannot be continuous, right? So that's a classification problem. And so today we'll be talking about models that like because so far we've talked about linear regression. And linear regression is continuous, right? It's it's continuous, but here we're talking about like some a model that produces like discrete labels. Okay. So we will introduce two common variants of linear classifiers, namely the perceptron and the logistic regression. So and like okay. See if I can get to those, but I'll see if I can get to that. Okay, this will probably be multiple parts, so like the name on the poster or whatever will have to change as we go, but yeah. Okay, so a linear classifier is a class of learners, as I said, like for like employed for classification-based tasks, right? So that is like it's used for a specific set of features corresponds to, right? And so we'll begin our discussion by talking about like binary linear classifiers, right? And binary linear classifiers are where like the data set is has its target, the output is constrained to one of two values, right? So like I am predicting like spam or not spam. I am predicting I am predicting my brain is blanking right now. Very easy. I am predicting, am I David or not David? I am predicting
The weather.
weather's not continuous though.
You could
Well, unless you're saying like, oh, predicting sunny, like you like are you predicting sunny, hail, windy, right? Like these are discrete labels, then sure. But if you're talking about like oh, relative humidity, right? That is now continuous, right? So you can sort of see like how different like even data sets can be like you have to sort of define a problem, right? Okay, yeah.
For you said that sunny tail, isn't that more than two? So it's not binary.
So it's not binary. It's not. Oh, sorry, my bad. Yeah, it's not binary. Sunny or not sunny. There we
Is that
go.
multi?
That is multi-class, indeed. Correct. Yes.
So essentially, it's just we need to have a Boolean output for.
Exactly.
whatever our
Correct.
model is.
Precisely.
Makes sense.
Fantastic. Yes. Great. This is telling me you guys. Okay. Good. And so the standard binary linear classifier, let's continue, is like involves two components, right? So the two components it involves is a linear response and a classification function. So, and so the binary linear classifier is defined, I should have used Blackboard before, but the binary linear classifier is defined as follows, right? So it's defined as y hat equals f of r of x, right? That's how I like to think of it. People won't notate it as such, but it's like this sort of really goes to show that I'm really trying to show you that it's just a math. Like people like to complicate things. It really doesn't need to be complicated. It's a function. It's a composition function, right? So y hat is your prediction, right? Like, are you predicting 0? Are you predicting 1? In this case, I've actually okay. Scratch that. The linear response r. So y hat equals f of r of x. So r, what is r, right? So usually, like when you evaluate a function, you go inside out, right? Like composition. So what is r? R is your linear response. R is a function that maps from Rn to R, right? It's a function that maps from the space Rn to R. So, and what is a function we know that already does this? Yes, precisely. And it's also why we call it the linear response, right? Like, linear response is effectively like your linear regression model, right? Like you get some X transpose, right? And then you augment it, right? So for example, if I have some data point, remember I have some data set xi, yi, I get a single xi, right? And that's like some n-dimensional vector. I will augment it by 1. By augment, I mean literally just add a 1 on top of this vector, right? And then I will perform my regular linear regression, right? And yeah, that's my linear response. So it takes this n-dimensional input and outputs a real number. Does that make sense? Good? Okay, great. Yes.
Is the parameter vector just a bunch of weights?
Exactly. Correctly. Right. Correct. From theta 0 to theta n. Yes, as we've talked about. Correct. Now, the classification function f is a function mapping from R. Well, there are two ways people like to do it. And I forget why I chose this way. I think the math worked out nicer when I was doing some sort of or the explanations worked out nicer when I did it like this, when I did the actual math on my notes. But the classification function f, as the name sort of implies, is where the classification happens. Like, because you've mapped, right, x to rx, which is a real number now, right? And now from this real number, you want to produce an output. Is it spam or not spam? Is it David or not David? Is it sunny or not sunny, right? Well, how do you go from this this real value number to that? Well, you employ the classification function. As the classification function sort of is defined, it needs to be something that maps from the real numbers to 0, 1, right? And like the set containing 0, 1. I don't mean like 0 in like the interval 0, 1, right? I'm being very explicit here. It's the set containing 0, 1, or the set. The second definition is you're mapping from R to -1, 1. That's the definition I take. Like, so for example, and so, well, I'm being very sort of vague as to what f is. There's a reason for that. But I'll get to that in a bit. So remember that, like, we sort of, okay, there's also alternative representation. So remember, like, linear regression model, I said it was like r of x equals theta 0 plus theta 1 x1 all the way to theta n xn, right? I might represent, like, in a lot of machine learning literature or whatever, or you look at textbooks or whatever, like, they won't represent your linear response as such, right? They'll in fact represent it with, like, they'll turn the theta 0 into b, and then they'll turn your theta 1, theta 2, theta n to w1, w2, wn. Can anyone sort of infer what b and w mean? You should know, because you just said it.
Weights and bias.
Correct. Right. Precisely. You just said it. right? So it's the same thing, right? When people refer to weights and biases, it's the same thing. Okay, good. So like this is a sort of, this alternative representation of weights and biases is like more, seen more commonly in neural networks. Does that make sense? So we'll introduce two types of linear classifiers. We're going to introduce like a perceptron, right? And then a logistic regression model. So like, yeah, binary linear classifier, two types we're introducing, perceptron, logistic regression model. Good? So you see the taxonomy, right? And a binary linear classifier in general is a function that maps from what? That maps from some x, right? Which is an Rn to a real number, and then from the real number maps to a actual decision. You first, Gotham.
Let's say logistic regression.
We're good. As I said, we're gonna get there. Take a breather. You're good. Yeah.
And just because, just to make sure, because I, whatever, last time was my first lecture, so the B and the W in this case, the bias and the weights are literally just the coefficient
Correct.
shape transforms of all your inputs, and then the bias is the, you know,
If you
moving it up and down.
moving
side
up
to
and
side.
down, moving it up and
Up
down.
side to side,
Yeah.
sorry.
Move. Oh, well,
Down.
not side to side. Up,
Not side to side.
Up,
corrected
up,
myself.
only
Yes,
up
I'm
and
down.
only up. and down.
Normal.
Because if you put, yeah, you know for sure it's not side to side, because if you set all these to 0, right?
Yeah.
Then the only thing that remains is
Yeah.
dots, right? It's
You
just a
can't
y equals m
Move a graph side to side by, you know, adding or subtracting some number from it.
from the inputs, correct?
Yeah.
Yes, great. So, okay, we'll introduce the perceptron first, right? So the perceptron is a linear classifier where the perceptron is a linear classifier where the classification function f is the threshold function, right? So the threshold function is defined like, the threshold function I define here is t, right? Some people also notated it differently or whatever. So it's f equals t, right? Such that it maps from minus 1, 1. So note that like I have chosen this notation here, right? I forget why forget why I did it. We'll see as we go. And maybe I'll just go, oh, I remember why I did it there. But as you can see, I try not to remember this. Like I try not to like memorize this stuff, because memorizing this stuff is bad. Like you need to know this intuitively, right? Like intuitive, right? Like try and understand, because like it makes explanations like these like a lot more free flowing and more fun, honestly. Otherwise I'd just be stressed. So the threshold function is defined as t of x equals 1 if x is greater than or equal to 0, and t of x equals minus 1 if x is less than 0. So like the people on the left who can see, it's literally less. This function. Good. Everyone know how to read this function? Otherwise you'd be struggling in your calculus class, and that's no good.
Is it a step function?
It's pretty much a step function, right? Like it's a piecewise function, right?
What is that? What role does a threshold function play?
Right, so great question. Give me a sec. Actually, I'll answer that right now. So remember, your binary linear classifier is defined as y hat equals f of r of x, right? So your prediction is this function f, like you apply the output of r of x, right, as input to f, right? In this case, I'm saying f is this threshold function, right? F is t, which is this threshold function, right? So the output of my linear regression model then is served as input into this thresholding function, right? So by that was actually my next point. Can someone tell me in what circumstances will the output of this perceptron be 1? I know you know, just give me, actually, yeah, go. Yeah, go.
Well, it's given this classifier function, if the linear response is greater than or equal to 0,
Precisely.
then it'll be classified as the whatever class is.
Precisely, correct, right. So when your linear response is greater than or equal to 0, namely when your theta 1 plus, when your theta 0 plus theta 1 xn plus theta 2 xn plus theta n xn is greater than or equal to 0, that's your output of your perceptron 1. Does that make sense? Okay. And otherwise, like if your linear response is less than 0, if theta 0 plus theta 1 x1 plus theta n xn is less than 0, then your perceptron is going to output minus 1 in this case, because I defined it to be minus 1. Some people will do 0. Right? Some people will say the threshold function is 1 if x greater than or equal to 0, 0 if x is less than 0, in which case you are adopting this first notation. Does that make sense? So, um, so like any classifier, I haven't introduced this, but like any classifier, the perceptron determines a decision boundary in feature space. So can anyone sort of intuit what, like, by the name itself, what a decision boundary is? Yes,
Above what threshold will it make a certain decision?
correct. Like at slight correction. At what location in feature space will you make a decision? Right. So remember my x1, xn, x1, my x's, my input x into this into this classifier is a n-dimensional vector, right? And my n-dimensional vector forms like like an n-dimensional vector lives in n-dimensional space, right? Like so, if I have like a three-dimensional vector, I live in three-dimensional space, right? Or if I have a two-dimensional vector, right, which is like xy points, well, I live in or x1, x2 points to keep notation consistent. If I have two-dimensional vector, I live in x1, x2 points.
Damn, world.
Brother, I'm not letting you. What are you doing, bro? Sorry.
was he doing?
That was a very disapproving head shake.
He's just trying to
Unless
get
he actually was here before, but if not, then no. Sorry, my bad. Where was I with this? Okay, so right, your decision boundary is the location at which it like defines where your classification changes, right? So remember that each input into the classifier is like this vector x, and the vector x is in Rn, right? It's a point in n-dimensional space, and let's say our data set, like we have two features, right? Like we have two input features, right, to produce one label. So your two input features are x1, x2, right? And so your points live on this x1, x2 space. Right? And the idea of the decision boundary is like, let's say I sort of draw a line, right, somewhere here, right? It doesn't matter what this line is. What I'm like, and let's say like above here, right, in this region, it predicts 1, and then in this region, it predicts -1, right? Well, this line I'm saying is the decision boundary. It is the location, it is the x1, x2 values for which your classifier's decision will change. Yes.
So the function, all it is basically just a function that just categorizes which category like input falls in based on like addition.
Okay, so confusing two terminologies, but technically the way you phrased it is also technically correct. But I'm going to stick to my way, and then I'm going to relate it to yours. So the classification function is this function f in this, okay, in this equation I've given you, right? It turns a real valued number into a decision, into sunny, not sunny, 1, 0, 1, -1, right? People do, because people think of it as Boolean, they'll do 1 and 0, but like in this case, my 0 is just -1, right? So sunny is 1, not sunny is -1, right? So your classification function is a function that maps the output of your linear response to -1, 1.
So basically,
Right.
the classification function just puts out a binary.
Binary output, correct. Yes, that's why it's a binary linear classifier, right? And a perceptron is one in which your T of X is that. Understood? Cool. Yes.
I know this might be a little bit ahead, but is the perceptron more for discrete and the logistic more for continuous? Since it uses the sigmoid rather than like just the step.
So, well, ultimately they're both linear classifiers.
Mhm.
So no, they produce binary outputs regardless. Okay, like the logistic, well, we'll get to it. We might have to do it in another lecture or whatever, but logistic regression is you have I'll just very quickly run you through, is where you have a linear response, right? You get your input value x, you have a linear response r of x, and then you apply the sigmoid function to it, right? And that is but then on top of that, you still have a classification function, right? So really, your R is now really like a composition of like a linear response plus your sigmoid. Does that make sense?
Okay, so it still outputs a discrete even though it's using.
Yes, precisely. Which is why it's it's a confusing name, right? It's because you see a regression, you're like, shoot, where's the regression, right? But it's not regression. But to continue on with my point, so classification, right, or the classification function is this function f that maps from R to -1, 1, right? But your decision boundary, right? So there's two things, right? So I just said a function, right? This function is what takes us from this output of our linear regression model or our output of our linear response to a actual classification, right? Sunny, not sunny, right? From minus, like I give you an input minus 125, I can give you sunny, not sunny, right? In this case, it'd be not sunny, right? What I'm saying now is like every linear, so we're moving on to a different concept. We're moving on, well, but related. Every classifier has something called a decision boundary, right? A classifier is just a model that produces these sort of discrete outputs, right? Every classifier has something called a decision boundary, right? And a decision boundary, right, is, as the name implies, a boundary where the decision changes, right? So it is like, yeah, think intuitively. Don't think too hard about like, ignore the math, just think conceptually, right? It's a boundary where the decision changes. You can imagine, right? Like for every, like in this case, I'm saying we have two-dimensional.
Is it just a threshold?
Yes, like it is effectively like a certain threshold, right? Yes, but I'll sort of intuit this a little more as we go. But like for x1, x2, right? Like for given x1, x2 point, right? I'm located somewhere in this feature space, right? This is like house prices and oh, wait, no. This is like years of education and median household income normalized, right? Somewhere like this, right?
Wait, is that what X1 and X2?
Right. Let's just say it is. Let's just say it is, right? Well, then my decision boundary is the line, right? Or some sort of boundary, right? It doesn't have to be a line. It's just some sort of boundary where for values on one side of that boundary, right? I am saying that, oh, actually, let's just say, let's say our x1, x2 is like, yeah, years of education and what was the other one I said?
Median household.
Median household income. And let's say like, whether the house is a good house or not, right? Because it's fine, it's classification.
House quality?
House quality can be like continuous, right? Because you might give it a 0 through 10 star rating or whatever, right? Let's just say it's good house or bad house, right? Based on some arbitrary, based on like my perception, right?
House is good match for income.
Or whatever, right? Like you can imagine like some sort of binary thing, right? It doesn't matter, right? It's a motivating example. It's just like I'm trying to give you a theory. On one side of this boundary, right? Like we could say this is a good house. On the other side, it's bad house. Okay, right? That's all a decision boundary is, and every classifier has that, right? Because at some point you have to determine whether it's a good house or bad house, right? Does that make sense? Okay, cool. And so what I'm saying is that where does this where's like what is the sort of equation of this decision boundary? Can someone sort of take a guess? What is the equation of this decision boundary based on what I've sort of told you so far? This is not easy. If you can get this, I had to think about, or how to say, like I had to think about this for a bit, but then when you're like, oh shoot, like that makes a lot of
Is it a
sense.
step function?
No.
Damn.
Right. I mean, sort of how I've drawn it already. It's a line, right? Like so like it has to be some sort of linear function.
Is it a straight line?
That's what I said. Yes. So it's a straight line, but I'm asking for the specific equation. Like based on this perceptron model that I've given you, in which the classification function is this thresholding function t. Can you give me the equation, right? Where my decision changes? right? Where at one side of the line, I'm predicting 1, at the other side, I'm predicting -1. Fix that.
If function is greater than equal to
It's-
certain value, it's
Well, it's not an inequality because it's a line, right? Because a decision boundary is a line, right? Or like it's a line, and then on one side of the line, it is one value. On one side, on the other side of the line is another, right? So it's just a line. Right.
but isn't that kind of what an inequality is? It's just true if it's
Yes,
above
but
a
I'm
certain-
asking for the equation of the line. So
So,
yeah.
like in the case of this, of T equals X, your perceptron equation over here, the decision boundary line would be Y equals 0. In this case over here, I'm trying to, like, it would be just like Y, it's just. a
the
line like
decision
that.
boundary in this case, or my thresholding function outputs 1, right? Outputs a certain class when X is greater than or equal to 0, and outputs a different class when X is less than 0.
Yeah, so then the decision boundary there is X equals 0.
You're getting somewhere, but I want a more, I want
For this.
for the perceptron. What are
Okay.
like in feature space?
Yeah, I'm just trying to get there. Okay, so then this would be.
In I'll give it like 10 seconds.
Does X equal 0 count, or it's like just
No.
a vertical line?
No, because what is X in this case? Because yeah, actually, yeah. I'm saying with respect to feature space,
Oh.
right? So like if I give you an x1, x2, right? What is the equation that tells me where my decisions will change?
Our product is 0 of X1, X2. Right? Of course, the.
You're using dot product, but not, but you can't dot product like.
Right.
Okay. Okay. Take a step.
Theta dot x equals 0.
Correct. Correct. When your linear response is 0. When your linear response is 0, that is precisely when your decision will change, right? Right? Because when T of X is 0, right? Oh yeah, yeah. That's my response to when I got that. Like, that makes sense. Right? When X is greater than or equal to 0, I'm predicting 1, and when X is less than 0, I'm predicting -1. So obviously, as you said, as you correctly noted, when X equals 0, that's when my decision changes. But when does X equal 0 with respect to x1, x2? Right? It is when my linear regression
Okay,
model is
cool.
outputting 0. Does this make sense? Cool.
And if you have taken diffie cues, that's heavy side, and then that one is Didac delta, but with matrices.
So what we can sort of imagine, what we can sort of imagine then is why I've sort of drawn it like this. You see, at this point, if you see like me draw it like this, you can sort of imagine that I'm gonna add a third dimension, right?
Is that what they call it, hyperplane?
The-
It's already hyperplane, right?
I am going to show you a hyperplane, right? I'm gonna try and draw this. I'm not an artist, unfortunately. I really wish I was. When I was a kid, I wish I tried so hard, but I was never good enough. So I went to the next best thing, drawing graphs, right? Wow, that was so sad. I don't know if you guys can see what I'm doing.
Please, please, please. That's a hyperplane.
I've just drawn a hyperplane representing my linear response for any given x1, x2 point. Does that make sense?
Yeah.
I give you a point x1, x2. My hyperplane, I give you a point x1, x2. My linear response is defined as this hyperplane, right? And when this hyperplane intersects 0, right? Which is when my linear response is 0, as we were talking about, that's where the decision occurs, right? Oh, yes, beautiful. Yeah. So that's actually what we're getting. That's actually the coding example we'll get to, right? Hey, it's drawn equally as well. What are we doing here? Don't clown my drawing. What are we doing? Okay. So, but you just saw the graphical, like the very nice computerized graphic example, right? When x is less than 0, right? Or when this linear response is less than 0, when r of x is less than 0, I am predicting one thing. And on the other side, I am predicting, on the other side, I'm predicting 1, right? So you can, in fact, additionally, is that a, oh, I'm getting this sort of head tilt? Fantastic, beautiful. I love that. I love hearing that. That puts a smile, that puts a smile on my face. We can then, I am drawing 1s and -1s on the c-axis. Imagine that sort of at this point, like, I can't draw this. This is where my ability to be an artist stops. But you threshold it, right? There is like above this, or when x1, x2, when the linear response of this x1, x2 point is 0, like above that line, the output is 1, right? It's a flat. The output is 1. It's a flat plane, and below that line is -1.
All right.
So you can sort of see there's a gap, right?
Yeah.
And the decision boundary is gap, which is like this, and also looks like that. Yes, this is what we're getting.
Take the diagonal line and turn it into two stacked right angles.
Look at that.
Yeah.
Just that. Just that.
So that one from the previous one was a smooth slope like this, right? But then you apply like the heavy side function to it. And then what that does is it makes anything below 0 become 0. Like in this case, it makes it become -1, right? And then anything above that becomes 1. So on that decision boundary, like where it was 0 now, nothing lives there and nothing lives like anywhere in between. It either lives at 1 or at 0.
So that thing is just a boundary.
Yeah,
Yeah.
yes.
Yes, sir.
You could write it as an if. I think I wrote it as an if in my code.
Yeah, you can totally do that.
I don't know why you wouldn't write it as an if in your code.
There's
What?
surely
How
like
else would you write it?
No, there's a NumPy vectorized way you can very much write it like that. And I mean, it does all these comparisons, but it does it so quick. Right? Because there's whenever you use NumPy, it's just the fastest thing. Don't fight it. Don't fight it. Don't try to do it yourself.
I'm lazy.
You would sound very stupid if you did. Because there are guys who are much smarter than you, who have spent much of their lives spending on optimizing this sort of library, right?
Me when I can sort by columns and pandas, me happy.
Okay, does everyone sort of understand this? That's fantastic, because that's sort of like the key of what a classifier is. And so the perceptron is, and how am I doing so far? Is this good? Great. Like, do I sound like an actual lecturer? Yes. That boosts my ego a little. I needed that. It's been a little rough the past few days. So when x is greater, okay, so some people have also learned that like this threshold function might be defined a little different, right? Namely, it is when some people might have learned elsewhere that this is like a sort of spot the difference game. Threshold of x is 1 if x is greater than 0, and -1 if x is less than or equal to 0. Versus when threshold of x is 1 if x is greater than or equal to 0, and -1 if x is less than 0. Like the difference is like this x equals 0 spot, right? My question to you is like, how do we sort of resolve this ambiguous output, right? Like based on the definitions, right? Like, what do we sort of do here?
Choose one or the other depending on what your data is about and what you're trying to classify.
I propose something even better. You don't care. At the decision boundary, you do not care. Under one condition. You do not care under one condition. You do not care under the condition that this is continuous, that your features are continuous, or at least one of your features is continuous. If I'm being very mathematically precise. Because when at least one of your features is continuous, the probability of you landing along this decision boundary, what is it? 0.
100%.
Well then you're just randomly classifying.
Yeah.
No, 0. The probability of you when at least one of your features is continuous, the probability of you landing on the decision landing exactly on the decision boundary is 0. Effectively. So
No,
for all,
Zero.
yeah, it is.
Is it like 0, or just near 0?
No, it's 0.
Hardware rounding errors will make it 0.
Oh, okay.
Even
No,
if like
it's not even that.
Your computer will make it 0.
Well, it's not
It's
even that.
also-
It's like statistically speaking, probability that, like, for example, the probability that, if I define, if you take in statistics, if I define 2 random variables,
floating
right,
errors.
x1 and x2, the probability that your x1 equals some x1 and x2 that lies exactly on this line is 0, because they're continuous.
Infinitely as many, because they're
Exactly,
continuous, you can't,
right.
yeah.
It's uncountable, your x1s are uncountably infinite, right? So your probability of landing on exactly one of them is 0, right? So who cares? Who cares? Who cares if it's continuous? If it's not, then okay, you actually have to think about it. But then you wouldn't like. But then like your linear response is like already kind of it's discrete data then, right? Like
Yeah.
it's weird.
You wouldn't use you
That-
wouldn't
that's-
use this to solve
That's
discrete
just
data.
that's just weird as crap. You wouldn't use it, right? So yeah. But does that make sense?
Yeah.
Yes. Okay. So. Okay, let's see. Okay, so we can also talk to like so this is the standard mechanism of the perceptron. So now at least you know one linear class line, right? You know like one linear class. We haven't talked about training yet, so we might have to do that next time. But I wanted to make sure you realize you guys really got this. So to this, okay, we can also talk about like representing nonlinear decision boundaries. Perceptron. Can someone sort of have an idea of like, what we might do? No, remember what I was talking about at the beginning of the lecture.
We can feature transform our decision boundary.
Boom. Yes, correct. Yes, beautiful. Yes, precisely. I can perform feature transforms and do the exact same thing, right? And now I can induce some sort of nonlinear decision boundaries. Let me read. Do I want to go through this? No, I do not. I don't have the mental to do this. Yeah, long story short, define a good feature transformation, and it's the same thing. It really is the same thing. You can sort of imagine, like, if I believe my decision boundary, for example, is a circle, right? Give me a sec.
Well, anything within that circle is 1.
It is 1, and then everything outside of the circle is like -1. Then what I might do is perform a feature transformation from the data points x1, x2, right, to the vector 1, 1 x1 squared plus x2 squared, right? Because then when I perform my linear response, right? So I transform my data set with this, right? So I get some sort of D transform. That looks like one x1 squared, x2 squared. When I perform linear regression on these vectors, right, I will get something that is 0, or when I calculate my linear response, it would be x transformed theta 0 theta 1 squared. Does everyone get that? Just the top. Hi, Professor Eiler. Yeah. So,
Lock in.
okay, wow. I need to lock in.
Lock in.
I need to lock in. Okay. Yeah, so where was I? Right, so if I believe that my if I believe my decision boundary is a circle, right? Then I define this feature transform like that maps from x1, x2 to 1 x1 squared, x2 squared, right? Because that results in like if I give you like an x1, x2 pair, then I map to 1 x1 squared, x2 squared. And then when I calculate my linear response, right, it gives you this form, theta 0 plus theta 1 x1 squared plus theta 2 x2 squared, right? And then as we talked about, right, like we apply this to our we apply a classification function, right? Above when our x is greater than or equal to 0, right, we predict 1, and when it's less than 0, we predict -1. So when this is greater than or equal to 0, I predict 1, and when it's less than 0, I predict -1, right? And so you can imagine that produces a circular map, circular results. Does that make sense? So, okay, to sort of briefly recap what we've gone through, we talked about like what binary linear classifiers are like and how we can like sort of mathematically think of them, and like how we use a linear response and a classification function to produce like, classification. And then we, well, at the beginning of the class talked about like what like or recap what feature transforms were, right, from last week. And then now like and then we related that to like how we might apply that to our linear regression example, right, to model quadratic data using this linear regression, like using our y equals mx plus b, but then applying a feature transform then on the data set. And then now we are saying we can do the same with our linear classifiers. Yes.
So given this exact example of your data might be like one class is in a circle and one class is outside. So because basically so if the data is in that circle or like an ellipse, say the theta 1 x1 squared plus theta 2 x2
It
squared.
can't model an ellipse right now, right? Because the decision boundary is purely going to be circular in this case, right? Because the form, like when I apply my, if I have x1, x2, right, and then I map it to 1 x1 squared, x2 squared,
Mhm.
right, and then I calculate my linear response in the same way I would with linear regression. In this case, my x1s and x2, my x1s through xn's is now x1 squared, x2 squared, right? When I actually expand this form, it becomes theta 0 plus theta 1 x1 squared plus theta 2 x2 squared,
Yeah,
right?
then, well,
In which this case, it literally is a like the decision boundary literally is a circle.
wouldn't it be a circle if theta 1 and theta 2 are equal?
Oh, sorry, I lied. You're right. No, it can't be ellipse. My bad. I'm trolling. If theta 1 and theta 2 are not equal, you're right. You're right. My bad. Sorry. But if they're equal, then it's circular. If not, it's elliptical. I believe.
So then, wouldn't so if you're given this step function as your classification function, is the bias basically like essentially kind of the radius
almost.
boundary?
Yeah, like if theta 1, theta 2 are like equal, then like it's like that square rooted is your
Yeah, it's a
Radius.
radius squared.
right. Yeah. So that square rooted would be radius.
Okay,
I don't remember like for elliptical functions like what exactly like that would
Yeah, I don't
represent,
know.
but like yeah, but you get it's elliptical.
So that's the purpose of the bias, is to like normalize it with 0 and 1 being the, or like above 0 and -0 being our classification boundary for our classification
Sure.
function.
Yeah. Okay. Any other questions so far? Does this like make sense? Because this is pretty important.
Actually, I do have one question. So that feature transformation for the decision boundary, that's only for the perceptron, because, or does it also apply to the logistic regression?
You can apply it to logistic regression models. Any other questions? Okay, great. Right, so we also talked like this relates to like our feature transform lecture again, like why not just like spam like why not just define a feature like okay, we talked about like okay, if we define a feature transformation that like increases the dimensionality of our data set, like and that makes it like more easily modelable by our data, by our model, right? And the sort of initial question people might ask then is why not just define a feature transformation that like maps through like a whole bunch of like or like raises my my components to like a really high degree power, right? Like for example, I have x1, x2. Why not just do like x1, x like create a mapping from x1, x2 to 1, x1, x2, x1 squared, x2 squared, x1 cubed, x2 cubed, all the way to like whatever nth degree power I want. Why wouldn't we do that? Why is that like sort of a bad idea? Yeah, precisely. Like, yeah, now your model's more flexible, sure, right? But you have a lot of parameters, right? And like it's likely that like you'll when you do training, like you'll fit perfectly on sort of on training data you have, but that learned model is like will capture noise as well. And when you reproject onto your original feature space, the and actually try to use it for new unseen data points, that model you learned would be terrible, would be absolutely terrible. So that's why you would do it. So you can't just like, oh, throw a bunch of dimensions, like oh, let it do the trick. It won't. You'd have overfitting.
Because essentially, if you spam dimensionality, then you've essentially maximally fitted your data set, which is it's going to make it the most possibly susceptible to any sort of small noise pattern.
By increasing dimensionality, you have moved the data points to a space where they are perfectly linearly separable, right? But then when you and sure, like when it reprojects back onto this original space, it produces this like really weird complex decision boundary, sure, right? But that took into account all the noise that was like part of the data, right? And then when you give it a new data point that like doesn't fit that pattern at all, right? Well, now you're cooked, right? Well, now your classifier is cooked. Right? Does that make sense? Do you want to get to coding? Would you like to?
Up to you. We can do it right now. We can do it later. If you've got more to talk about, we can speed run it.
What do we feel? What is chat feeling today? You want coding now? It's up to you guys.
One's in the chat for coding, two's
Yeah.
in the chat.
Yeah. What?
Yeah,
Raise your
hands up if you want
hands.
code and hands up if you want more.
Hands if you want code. Hands if you want code.
All right, hands up if you
Well, I guess
Yeah.
software engineers habits die hard, eh? Yeah, okay. All right. So sorry for
What do you mean
yapping too long.
die hard?
Sorry for yapping too long, I guess. My bad. My bad.
We'll run through it. It'll be quick.
Hope this all made sense, and if it didn't, feel free to like step outside for a bit, ask me questions, or if not, like ask me after this as well. Good. Thank you so much for listening. Yeah. Okay.
Enemy, Christian mic work.
Yeah. Actually, I should probably erase this because we we definitely left a mess last time and people were probably not very happy. So does anybody want to like take pictures of this or not take pictures of this before I start erasing
No,
it?
give them the gift of knowledge,
You get
Austin.
a, you get a little.
Let me get out of the way first.
How do you display?
Including my. Bro, if I knew, I would have done that like every time I've been here. But it's been 2 years and I still don't know how to work this.
Yeah.
All right, everyone good with the board?
Oh,
Good?
we'll call it good.
Okay, we'll call it good. I mean, if it's not good, just ask me.
Wait, so is that or is this what's gonna be?
Oh no. Oh no, that's bad.
Okay, so it's that one that's gonna be on there. How's it work?
Dude, we don't have.
Where does this live? Oh, okay, perfect. Awesome.
Oh boy, I can see my.
All right, this is in the Discord. If you want to take a look at it. So, all right, quickly. So first, we need the sigmoid function. Remember, we were talking about it. This is the thing that maps values from whatever we have to 0 to 1. So, do you have the pen? Oh, you do.
Yeah, it's fantastic.
Yeah. So if you don't know what this function looks like, it's something like that, where this is 0, this is 1.
I think it's very shifted to the left.
It is, but this is the general shape.
Correct.
Okay.
Correct.
Yeah, sorry.
Correct.
Very
That is so
one word shifted
Like
over.
right there.
That is so shifted to the left.
I mean, yeah.
Don't criticize my drawing, okay? This is why I'm not Plotly stuff.
Yeah, this is why we decided not to be art majors, right?
Yeah,
Yeah.
but that's the general idea, right? Any questions why we need to do this? All right, perfect. So you all understand that it's because we're going to be representing a probability, and probabilities are from 0 to 1, and this does that.
Oh yeah, so this
Oh,
is
okay,
wait,
awesome.
very quickly. So like we talked about perceptrons, right? In which it takes this form like y equals f of r of x, right? And in this case, this was like where I was alluding to, right? Like where I was headed, right? And like we didn't get to y, right? Because I like to take my time and make sure everyone gets it, right? Because you can train with this, right? You can actually calculate. So long story short, why we sort of motivated everything we have the way we have, right? Is because like you can't perform gradient descent on the thresholding function, right? Because what do you do at x equals 0? But you can, right? And also like think about it. Look at the threshold function t of x, right? What is its derivative? It's 0 everywhere, right?
No.
It's 0 everywhere except at x equals 0.
Yeah. Where it's infinite,
Right.
and you can't calculate that.
Right. And so that's bad, right? And so like actually like we like I was gonna show you like or I was gonna show you guys like the sort of cost function that's associated with the perceptron. Right? It's also known as perceptron loss, and then in which like okay calculating the gradient of that and then applying the stochastic gradient descent formula we talked about like a couple lectures ago.
I think I get to that.
Right? That gets you to what we call the perceptron learning algorithm, right? But the perceptron learning algorithm like has issues, which I was going to mention, but time constraints. Right? Okay, that happens.
Yeah, so this is the programming standard one, right? This is the one that almost everything we use for an output layer. Some of you may know another one that's commonly used in neural networks called ReLU. So ReLU doesn't work here because you need values from 0 to 1, and ReLU will just like keep going. So you can't use ReLU for this. And then there's a forward path. Does anybody have any questions about what this does? I feel like it's like quite obvious. It takes our features and our weights and our biases, and then we get an output, right? And then from that output, we slap it into this, and it gives you a probability.
Is EPS epsilon?
Oh shit, I didn't even get to compute loss, yes. But yes, EPS is epsilon in order to avoid divide by zero errors.
Oh.
Yes. Yeah, but it does stand for epsilon, correct?
Thank you for asking questions during that. That was Professor Eiler's my research advisor, so I kind of needed the ball out there, you know.
There you go. Easy, big baller.
Thank you, loves. That meant a lot to me, just saying. Yeah, my bad. My goat, by the way. Actually, like, yeah, again, he's the reason why I know all this. Simple as that.
Take his class. Oh,
Take his
he's not
class.
even he's not even teaching you this quarter.
He's not, but if he teaches, if he ever gives you, if there's ever 178 and you see Professor Eiler, it's hard. I'm not gonna say it's easy. I'm not gonna say it's easy.
But
It
you
was,
take
it
to
is
learn
so, if you like ML, if any of this sounded interesting to you, take it and push yourself. And do things that like you didn't think you could do. Ask so many questions. And because he will, after class, you stand out there for like 30 minutes and talk to him, he'll talk to you. He's one of the only professors I know that'll do that. Yeah. I don't know where I've lost that.
Any questions about the loss function?
Can you go over it again?
Okay, yeah, okay. So the way the loss function works here is we are looking at our predictions, right? And then we're looking at like what is the actual value we're getting. And then, you know, it's like, do you know like standard deviation formula where it's like y pred minus y actual?
For all of
Yeah.
the points?
Yeah, for all the points, boom, that's this. Right? Okay, plus like a little normalization. And then we don't want to divide by zero, right? So we throw in epsilon, which is, you know, very close to zero, but not quite.
Good question. Why does it look like you're adding epsilon? Oh,
I
wait.
am.
Oh, yeah, and also.
Correct.
Is loss some number between -1 and 1, or is it like?
Yes, so the loss is gonna be a number between -1 and 1, because remember, what did my forward pass return? My forward pass, yeah, so that value was like somewhere between here, so the loss is also gonna be somewhere between here.
Oh, it's between 0 and 1.
Yeah, because look, I take the mean of that too, right? So let's say you get like 0.1 loss and then 0.1 loss and then 0.1 loss over like 1,000 features, whatever. So my loss is like 100, and then I take the mean of that. So my loss is 0.1, right? So that way, like if we have features that are like very big or we have a very large data set, we can still be like on average, like my loss is like I'm off by X amount between 1 and 0.
Wait, it's loss. Wait, so it's loss from 0, 1 or -1, 1? I'm confused.
Oh, my bad. You are right. It is negative. It is negative because of the gradient descent. Later. You could remove that and then add it into your gradient descent later, and it wouldn't change anything. But yeah, you're right. Good catch. My bad. And then there's gradient descent. I mean, who doesn't know what this is? This is the way down the slope. Like, this is the optimization, right? Okay.
Does it calculate it any differently because it's classification versus
No.
regression? No.
If you want to see where the classification happens, because like we kept talking about like that threshold, the threshold is dead ass this line right here. That's the threshold line right there. And all it's doing is like, is the probability above 0.5? Make it 1. If it isn't, make it 0. So yes, I if statemented this. I mean, technically it's not an if statement, but you know, it's a Boolean cast, which is effectively the same operation. Yeah, so that's how you apply a threshold. I'm sure there's like more clever like bit shift ways to do this. I'm not even sure you're allowed to do those in Python.
It's probably optimized enough anyways.
Yeah, so I'm sure somebody at Python was like, oh, people keep doing this, like maybe let's just make it like a bit shift or something. Or you have hardware accelerators that'll take care of it. Like I know CUDA has one for this exact thing. And then training it's like, if you were here during week 5 or week 6 where I did linear regression, same story. Find the gradient, go down the gradient. If you overshoot, you'll go back up. That's why you make LR pretty small. So behold what happens. Yeah. So these are your training losses. Holy sh-
Ooh, what happened there?
Oh, my bad. It's because my learning rate. My learning rate was quite high. There we go. Obviously, you can keep adding like 0.000 to this or whatnot, right? To get more accurate, but this is like the basic idea, right? You move down like a guesstimate and then you keep going. And then there's your decision boundary. Again, it is an if statement on that loop. And obviously I'm not gonna go over these. These are like harder.
Why is there a red point in the blue area?
Because it's it's minimizing like the error, right? So it's minimizing the loss.
Okay.
So it's trying to look at like, what line keeps the net distance, like the net classification, like most correct. Technically, it's net distance, and then you throw on the classification afterwards. But yeah, if your data is like heavily intertwined, like it won't do anything. Because it'll just like if these were overlaid, these are randomized, by the way. They are just somewhere over here. Okay. Boom, my classes. They are the same class, same random, shifted. Okay. If these were shifted by nothing, 0, 0, the classifier, its error would stay basically flat the whole time, and the line would be straight through and you'd have red and blue on either side, right? It wouldn't do anything. So that's when you'd probably need like another classifier that's either higher dimensionality, or you'd probably need to do like a decision tree for that would probably be the right way. It's not really something you can do with, because inherently this assumes your data changes linearly, right? It assumes that like I have some variable X, which is impacting, something about my distribution, right? Things with bigger X are one thing, things with smaller X are something else. If that's not the case and X plays no impact, which is what that would be like, right? And my feature is X, then there's going to be no impact on the data. And I'm sure there's a really nice Bayes formula that correlates like, how much your variable impacts the thing and like how accurate you can get it. That goes to 0 if it's like not dependent on that variable. Does that make sense what I just said? All right, pause. Okay, if you have like data set 1 and data set 2. So X is like data set 1, right? So let's say I have like a bunch of X's.
Sounded like gobbledygook to me.
Right, and then let's say like circles are data set 2, right?
That's what's taught me. Too bad I can't read.
Right? And then this is like my X, this is my X axis, right? This isn't an X, right? Maybe that was a bad choice. But the accuracy that you can get with linear classification is dependent on, do you guys take stats? Do you know what the R coefficient is and what R squared is? Tells you, yeah, your correlation coefficient. That tells you like
Strength of the data.
how strongly that data can be explained by some variable, right?
The explanatory variable.
Your correlation coefficient?
No, like basically the variation in the data can be explained. Explained.
Is that not what your correlation coefficient says?
Oh,
Yeah.
X is your explanatory here, and then correlation coefficient is how close it is.
Yeah, right? So if your correlation coefficient R is very small, meaning there's very little correlation between like X and what's happening in your data, I could try to, make like a classifier based on X like as hard as I want. It will only ever be as accurate as that R. You can't get data to be more accurate than the ability of the data than the ability of that variable to affect the data, right?
Right.
You can't magically gain some insight about X if X doesn't have that impact on the data, right?
Yeah.
So linear regression can only ever be as accurate as R. So if you have really high R, great, you'll have a really high linear regression accuracy. If your R is like 0.5, like good luck.
Yeah, if 0.5 R, you're gonna have stormtrooper accuracy.
Exactly,
Yeah.
right? So the limit is as it approaches R. Obviously there's like some other problems you get in with that, but that's the gist. Any questions on that now? All right.
The clock is right twice a day.
You guys can take a look at the rest of the code if you want. The graphs so this is sigmoid, right? This is like, you took your weights, you took your biases, you took sigmoid. This is that probability right here. And then this is post if, okay? This is like the actual classification. So does that make sense, the distinction between the two? This is the raw output of the data and the classification, which is your probability of being either one or the other. And then this one is whether the output of your model says one or the other.
Okay, so if you wanted to just use the probabilities, then you don't need to use the hard classifier and just leave the sigmoid. But if you want the discrete stuff, then you just apply that.
Yes.
Okay.
So is all the difference between the two graphs is one is discrete, one is continuous?
What's the problem?
Discrete I mean, technically, this is still continuous, right? Because it has a discontinuity at 0, right? But from whatever those values of X are below that line and above that line, it is still continuous. Yeah, diffie cues are annoying. Yeah, it's not really, because this function post map maps a continuous domain into 0 and 1. And then the other one maps a continuous domain into values. Does that make sense? Okay. So the domains for both continuous. The range, not. Does that make sense? Okay.
Are you referring to a logistic regression model right now?
Pre and post classifiers.
Oh, okay, yeah.
Is that a hand? Is that a question?
No. I just like, are you done with the notebook? I just
Oh,
wanted
yeah.
to go over the loss function again,
Yeah.
if you could.
Holy shit, where is it?
It's like all the way at the top. Yeah, view loss right there. Can you like
Alright.
explain how we get there?
Yeah, okay. So you have your data, and your data is classified into it is or it isn't this thing, right? So for this example that I did, where is it? Here, class 0 is it comes from the random array generated by, 0, like 100 from values like 0 to 2 with like this shift.
Mhm.
And then the other one comes from 100 values with this shift, right? So those are my like 0 and 1s. And then I think the comments do like a fairly good job of explaining it, but you have a different loss for when your value should have been 1 and when your value should have been 0. So
Oh, I see.
if
because
the
each
distribution
component
came
gets-
from, if the true value came from a distribution where it was 0, you would use this equation, where you have the 1 minus in front of the y prediction, right? And then if it came from the distribution where the y should have been 1, you don't have that 1 minus, and that 1 minus is there to shift your data.
Oh, so the actual loss being computed is,
You need to compute your loss for. You basically do the loss of how wrong am I on guessing class A? How
Right.
wrong am I on guessing class B?
uh,
You add them together.
Weighted.
Weighted. Yes.
Why are you taking the negative mean of all the sample losses?
Gradient descent later. You don't have to have it here. You could keep it in the gradient descent.
Oh, okay, that's just a go.
Yeah, if you removed it and then you multiply your gradient descent by negative, like.
Oh.
I just,
You
This
just,
is
you
like
just did
also-
it there that way.
this is the standard way.
Oh,
Your loss, like, if you're computing a loss of a set of data points, you should be like computing the mean. Like, or how do you say it? Like, you compute the loss of your individual data points and then average.
Wait, no, he's asking like, why is
why
there
why
a
the
negative?
why the negative sign? But it's because he's doing the
Oh, yeah,
the
yes,
the
correct.
gradient thing then
Yes.
rather than
This is standard. Don't ask me. I feel like loss should be positive.
That's
I feel like the loss should be a positive value.
It should be.
Bro, when
who wrote this?
trust, I copied it. I copied this equation.
From where?
From Googling what is the compute loss? Because normally I would just like scikit-learn this away. Like I don't need to understand the
Sure.
implementation of
Yeah.
this, right? All I need to know is these things in, this thing out. Obviously it does make sense why it's there. And because like the actual equation for like gradient descent uses this loss, you could just leave it there. You could just not leave it there. This is standard and I don't know why, and I don't really care to know why.
Maybe it's just because it's faster to apply the negation on one value versus an entire like set of derivatives maybe? Like
From a
slopes.
hardware perspective,
I'm just
I
thinking like
don't think
I'm
that
thinking like a
matters.
computation like
It's
how long?
it would be 1 bit flip.
But like when you're dealing with like exponential like massive amount of
But okay, say you
Like
had like a
parameters.
computer, say you had a computer register, 64 bits. You need to apply this, right? You just do the whole thing, and at the end, you just take 2's complement of that thing, and boom, now it's a negative.
Bit flip, like if you're referring to like actual speeds, like of bit flip,
Like,
over a
on-
large arrays, like if it's stored, if your objects are, if your bits are stored in like memory cells, you can like, it's literally corresponds to turning electricity off and on along a grid of data, and that speed's conflict. You say it's probably faster for a grid actually than it is.
This probably came from some math guy.
but
I'm
I
gonna be
don't.
so for real.
but-
There's no way a CS major sat
Wait, no.
down and was like, chill. I'm gonna put the negative there. And also, like,
Oh, actually, wait, no, sorry. The negative should be there. My bad. So I was rederiving them. I derived the math on this. It corresponds to I believe performing maximum likelihood estimation on the logistic regression model parameters. So if that made no sense, I can go over. Like I plan on going over that anyways.
yeah.
But
What is that?
yeah, like there's a statistical justification for why your loss function is the way it is.
it's in the formula, like I just looked.
Well,
up
yeah.
the-
It's in the formula for negative log. So it's in the formula for negative log likelihood, but I wrote down an explanation for why why negative log likelihood is the way it is. Right. So we can go over that
It's
anyway.
got to do with the regression and linear descent later on, and that's why they leave it.
It's actually so. Let me actually read through what I wrote. I wrote this a long time ago. So
Chad, I copied off his notes and then I just put it into NumPy 4.
Who that?
But yeah, if you ask me on a stats test, I never write my loss with a negative. I'll be like, oh, my error
Oh,
is
right, so-
positive.
Yeah. So to explain it. So when you perform maximum likelihood estimation, you're argmaxing over like some sort of value, and argmaxing over a value is the same thing as the negation of argmitting over, like it is the same thing as argmitting over the negation, right? So if I'm trying to maximize something, it's the same thing as minimizing the negation of that. And so, as I said, you're trying to like you're performing a maximum likelihood estimation. We could talk about what that is, but to implement that as gradient descent, in which you are
the minimum.
in which you are iteratively finding the minimum, like you're performing like calculating gradients and iteratively
So it
moving
still has to
down.
do a gradient descent.
So
Like
you just
you need to convert your loss, like because we think of the loss function in terms of like or performing. Actually, yeah, no, like you're right. Actually, that
It is because of gradient descent.
it is because of gradient
Stand
descent.
Undefeated. I know the programming.
it's like
You know,
it's
just
just
a-
like you flip the gradient descent space and then gradient ascent because it's.
No, so we
Wait,
have.
gradient ascent is incredibly difficult.
I mean, just like going up instead of.
So
Are you talking about like
we-
the flipping of?
no, okay. I haven't introduced this, but it's called maximum likelihood estimation, right? And like there is a loss function that is based on maximum likelihood estimation, right? It's a statistical method, which and we'll get into that. But as the sort of name implies, maximum means you're finding argmax of something, right? And you don't want to find argmax of something. You want to find argmin of something because that's like how we think of our costs, right? And so we define our cost functions accordingly.
Does it make sense why we min, by the way? And like why
Yeah.
you do gradient descent instead of gradient ascent?
Yes, because we're trying to find the minimum of the loss. So we're trying to, since we're calculating the like ascent whenever you get the gradient, we just negate that so that we can go down. That way we can find and minimize the loss.
But also with gradient ascent, there's like a hardware limitation too. But also like if you imagine like you're going into a bowl, right? All your vectors kind of point the same way. If you were to try to do that with gradient ascent and you get stuck the wrong way, the multiplications, like you can do floating points down to a certain accuracy, right? But you can't do exponentiation up to whatever you want because at some point
Oh,
you're
true.
gonna
At
crash.
a certain point, like there's too much.
Yes, at a certain point you'll hit 64 bits and it'll be game over.
Yeah, and you'll kind of cook everything.
Yeah, you'll hit overflow and then it's
Toast.
rip, right? But if you go down with floating point numbers and your divisions get worse and worse and worse, right?
Then it's
Your
just
losses
floating
get smaller
point.
and smaller. At some point you hit floating point estimation error. And if that's the only thing holding your model back, it's like, dude.
Then you're probably
go-
fine.
yeah.
You're probably fine at that. If you're getting to
Good
floating
model.
point errors, you're probably fine.
Yeah, so that's like from a hardware perspective why we don't. You don't want to go up. Up is bad. Down is very easy.
Okay, so whenever you'd ever want to compute something going up, you just take the negative of the negation, the minimum of the negation. If you
No,
ever want, if you ever
find the
wanted
min
to
instead
find,
of the max.
Wait, sorry.
Yeah.
What's the
if
question?
you ever wanted to find like the argmax of something, since
It's the same thing, and from a computational complexity standpoint, I believe, like minimizing a function versus like maximizing the negation of the function is effectively equivalent. Let me see. I'm pretty.
If you standardize,
So
your
I'm no,
loss-
I'm pretty confident that's true actually.
If you
So let's
standardize your
see.
loss, you can make it a probability
Right, yeah.
between 1 and 0, and then you can take the complement.
Right.
And now, beautifully, you've never run into overflows.
Okay, yeah. For top cross-validated stack exchange answer, minimizing f of x is entirely equivalent to maximizing negative f of x in every aspect. Result, numerical precision, computational complexity, everything. So it's just a convention we showed of why we decided to define like loss functions as losses, right? Like as a lack as a lack of utility as opposed to like maximizing some sort of utility.
okay, so it's more so we're just turning the equation into something that makes more sense intuitively.
Right, but like there's a statistic, but as I said, like there's a statistical method in which like in which, so as I said, maximum likelihood estimation. like these logistic regression models use for their utility function almost, and then we want to augment over that, so instead we find like negative. Okay, yeah, that we gotta go, because